we were discussing this uncertainty principle and its derivation. I actually demonstrated the uncertainty principle as applied to position and momentum. For example, we saw that delta x into delta px is greater than or equal to h cross by 2. And I also told you that this is actually a special case of a generalized uncertainty principle, which says that delta A into delta B must be greater than or equal to minus 1 by 4 expectation value of the commutator of A with B. So, today we will spend a little bit of time. I hope I have got it right. If not, anyway, I am going to derive it, so we will get it right. And in the specific case of x and px, this actually led to the relationship that delta x into delta px must be greater than or equal to h cross by 2. Now, this is actually a peculiarity of quantum mechanics. See, in classical mechanics, it is possible for you to have a particle with a well defined position as well as a well defined momentum. Right. If I had this chalk piece and if I let it go, at each instant I know where it is, and I also can find out what is the momentum of the particle. So, there is no uncertainty according to classical mechanics either in position or momentum. You can define both at the same time to any precision that you want, but that is not what quantum mechanics says. Actually, if you look at this relation, this uncertainty principle, what it says is that there is no state of the system in which the momentum and the position are both well defined. There is no such state. In fact, if you try to construct a state with very little uncertainty in momentum, then as we have seen previously in the previous lecture, the momentum becomes very uncertain. I mean, we did derive an expression for delta x and delta p, and if you look at that expression, what we found was delta x was actually, I am not going to write the wave functions, but delta x, if I said delta x is equal to a, then I found that delta px was actually h cross by 2a. So, if you try to reduce the uncertainty in position by reducing the value of a, then uncertainty in momentum increases, right. Or if you try to reduce the uncertainty in momentum by increasing the value of a, that you can do, then what will happen is that the wave function that we had, it actually becomes very, very broad, making the position quite uncertain. So, let us now look at the derivation of this expression. The derivation is based upon an inequality which is referred to as Schwarz inequality. So, let me first tell you what this is actually. If you think of any arbitrary function u and another arbitrary function which I shall denote as v, these are two functions. If you, because we are thinking of quantum mechanics, we can think of them as acceptable wave functions. Okay. What I will do is I will take the first function, multiply it by a parameter lambda. So, lambda into u plus v, I am going to take lambda, I will assume is real, it is not a complex number. Lambda is real, but u and v are arbitrary, they may be complex. So, what I am going to do is, you can take this function okay, take its complex conjugate. I mean, to make things simple, I will I was going to say I will make it one dimensional, but it is not necessary. So, these are functions of any number of variables u and v. So, lambda u plus v. I am going to take the function, multiply it by its own complex conjugate, and then I will multiply it by the volume element d2 and integrate over the entire space. Lambda is just a parameter, and because you are taking this combination, the function, and multiplying it by its own complex conjugate, what will happen? The product, this is actually equivalent to calculating the magnitude of lambda u plus v and squaring it. That is what this object is, and this I know has to be positive, and therefore, if I integrated it over the entire space, what should I get? I should get a number which is definitely greater than 0. So, this has to be greater than 0, but it may so happen that I have some I was not very careful, and then what might happen is that I have taken lambda to be -1, suppose, and u to be equal to v, suppose, I mean by accident I chose that, then what will happen? This function will turn out to be 0, in which case I have the possibility of having this equal to 0, and therefore, I can very confidently say that this integral has to be greater than or equal to 0, right. And if that is the way it is, I can expand this. If you multiplied it out, you see lambda, well, the star operation you can take it inside, it is not going to affect lambda because lambda is assumed to be real. It will affect u as well as v. So, I will take this star operation inside, and I am going to get that. And lambda is just a parameter, it doesn't depend upon the position coordinates, it is something that you can choose any value, maybe 1 or 2 or 3 or 3.5, some number. But interestingly, whatever value you choose for lambda, the answer is guaranteed to be greater than or equal to 0. That is important. So, let us multiply this out. Well, if you multiply this out, you will have the product of these two, that is going to be lambda square u star u, that is one term, right. When you multiply, you are going to get that, because lambda into lambda is there, and then you will have the volume element d2, and actually the integral will occur here, but the integral I am going to put it here, because lambda does not depend upon any position coordinates, it is just a number, just a constant. So, therefore, this will be my first term, and I will have 3 more terms. One of the next terms will be lambda times integral du, sorry, not du, but d2 u star v, right, that will come when you multiply this with that, and then you will have another term which is roughly of the same form, lambda times integral u v star, correct, and the last term will be how much? It is going to be integral v star v d2, and this has to be greater than or equal to 0, right. That is actually something very obvious, and what I am going to do is I am going to say, okay, this is actually of the form lambda square into some capital A, where capital A is this, plus lambda times, well, let me call this capital B, then if you look at this, you would realize that this is nothing but B star, the complex conjugate of B, the way it is, this one and that one are complex conjugates. So, if I put this equal to B, that will be equal to B star. So, here I can say lambda times B plus B star plus this object, I am just going to denote it temporarily by the symbol C, and this has to be greater than or equal to 0. And it does not matter what the value of lambda is, this is greater than or equal to 0. You can give any value, whether negative or positive, it is guaranteed to be greater than or equal to 0, correct. So, you look at this is a quadratic in lambda, and you have to remember whatever you studied regarding quadratics. A quadratic is greater than, it is guaranteed that the quadratic is greater than or equal to 0. What does this mean? This means that this object, that I hope you remember, discriminant, okay, has to be negative. You remember that, I suppose it is, if I had a quadratic like ax square plus bx plus c, if it is guaranteed that it is greater than or equal to 0, that means actually b square minus 4ac has to be less than or equal to 0. This is something that I shall assume you know already, and therefore, if I just applied it here, what is the result that I am going to get? I am going to get b square. Well, in this case, you say this small b is to be identified with capital B plus b star. So, capital B plus b star the whole square minus 4 times a into c has to be less than or equal to 0. Right, and that implies that, well, let me write it in the reverse. Well, I will take this to the other side, that means for this left hand side is less than or equal to 4ac, or I will write it in this fashion, 4ac must be greater than or equal to b plus b star whole square. Or if I divide by a 4, I shall get this, right, straightforward. But now let me put back the definitions of a and a, c and b. What is a? A is actually integral u star u d tau, that is a, this is a. C is integral d tau v star v, that is c is greater than or equal to 1 by 4. What are the values of b and b star? Well, you have the definitions here. So, what will happen is integral d tau u star v plus integral d tau v star u. There is a square, right. Fine. And this inequality is referred to as the Schwarz inequality. Okay. It is quite useful in quantum chemistry actually. Whenever you encounter later on, whenever you encounter overlap integrals, actually you can prove inequalities regarding overlap integrals, but overlap integrals I have not introduced. So, starting from here or using this inequality, I will be proving that inequality. I mean, the way this inequality is, you can actually compare the two, and so you realize that somehow what I have to have is, I have to have delta a square here somehow, and I will have to have, if you compare the two, I will have to have delta B square here, and then I have to see what happens to the right hand side, and eventually the right hand side will work out to be equal to that. This is what is going to happen. So, how do I manage these things is the question. Now, this will take a few steps. Well, let me start with this operator A. Operator A, of course, we are doing quantum mechanics, so operator A is Hermitian. So, the moment you say A is Hermitian, I know that if you allowed A to operate upon psi, multiplied it by phi star and then the volume element d tau, answer will be equal to this expression. You allow A to operate upon phi, multiply by psi star, integrate over the entire space and then take the complex conjugate, right. In fact, if you took this complex conjugation inside, you can see what is going to happen. You will get d tau, this star and that star will make it just psi, then you will get A star phi star, right. This is what will happen if you took the star operation inside. And that is equal to integral d tau. See, what is happening is that I have to take A, take its star. What do you mean by taking the star? If A contains square root of minus 1, if it contains I, then you have to replace that with minus I. If A does not contain I, then you do not have to worry, it is just unchanged. So, if you like, you can write this expression in a slightly different fashion. You see, I have this A star, it is an operator, remember, operating upon phi star. So, what this says is take A star, allow it to operate upon phi star and then multiply the result by psi and integrate over the entire space, that is what it says. But now what I will do is, you see, I will put this A star phi star first and then I am going to put psi, but then of course this can be confusing because A should not operate upon psi. So, therefore, I will put a bracket here to indicate that this is operating only upon phi, right, not on psi. So, if you looked at this expression, see, if you compare these two, what is it that you find? If you had a Hermitian operator and if you had an expression like this, actually what you can do is you can allow A to operate upon phi star instead of allowing A to operate upon psi, but then of course not A itself, but A star has to be operating. You look at this, you see, this operator, it is at the moment it is operating on psi, but instead of that the operator can be operating on phi star, that is what it is saying, it can be operating upon phi star, but then it is not the operator itself, but its complex conjugate that has to operate upon phi star, you will get the same answer, right. So, therefore, you can put it in the other way, if I had an A star here operating upon this phi star, that A star can be transferred to transferred to psi, but then when you transfer it, it becomes A. See, if you had an expression like this, A star is operating upon phi star, but then this can be allowed, I mean from here it can be moved and allowed to operate upon psi. The answer is going to remain unchanged provided you take not A star but A, right, and this is useful. So, with this I am going to think of let me think of an operator which I will denote as delta A. Why do I call it delta A? Because I am going to say it is nothing but A minus the expectation value of A. There is nothing wrong in that. I mean, you are going to give me an operator, any operator, I will first calculate its expectation value and I am going to subtract that expectation value expectation value will be a number, in fact it will be a real number because this is our experimental answer, right. So, this object will be a real number. So, from A I will just remove that and then I have this operator, and now what I am going to imagine is that I want to calculate delta A operating upon psi multiplied by delta A operating upon psi star volume element d2 integrated over the entire space. Now, you may wonder why do all these things. The answer is extremely simple. This is actually nothing but, I am going to claim that this is nothing but delta A square. That is what I will show. This object, and that is the reason why I introduced this operator, otherwise there is no reason for me to introduce this operator. This operator is such that the uncertainty in A can be written as delta A operating upon psi star multiplied by delta A operating upon psi. How do I show that? Well, this is actually equal to integral of d2 A minus expectation value of A into psi. You have to take the star of that and you have A minus expectation value of A psi. Right. So, there are actually, I mean, if you multiply this out, you will realize that there are 4 terms there, correct. There are 4 terms. Let me look at the terms. The first term will look like what? Integral d2, well, A operating upon psi star and A operating upon psi. This is the first term. There are 4 terms, I am just writing the terms one by one. So, this is the first term, correct. It comes from this and that, I mean A operating on psi multiplied with star operation and then A operating upon psi, that is the first term. And this is actually equal to integral d2 A star operating upon psi star multiplied by A operating upon psi, right, straightforward step. But then I have already told you that if I had in A operating, A star operating here, I can actually allow this to be transferred there in general, because you look at what I have done here, for any arbitrary psi, if I had A operating upon psi multiplied by phi star integrated over d2, the answer is equal to this expression. And therefore, I have already told you, if I had an A star here, that A star can be transferred to psi, but only thing is that in that transfer process A star becomes A, that is all. So, that is what I am going to do here. I am going to transfer this A and allow it to operate upon this part. The only thing, as I have told you, is that in that transfer process A star becomes A, and therefore, what will happen? This is nothing but integral of d2 psi star A square psi, or what is that? That is nothing but the expectation value of A square. So, that is my first term, right. Then you look at the next term, there are 4 terms, so you take the next term, which one should I take? Well, maybe this with that, this into that into psi, and psi star of course. So, that will appear with a negative sign, the negative sign you are going to have minus integral d2. What are the terms that you have? Expectation value of A into psi, expectation value of A into psi, you have to take its complex conjugate, and then you will have A psi, right. This is one of the next term, correct. And what is going to happen is expectation value of A is just a number, right. If you calculate the expectation value, this is the average of a large number of measurements, it is just a real number. So, this number is not affected by the integration, so I can take it out. So, what will happen? I will have this object, right, because I have taken this expectation value outside. So, the expectation value has come out, then I have psi A operating upon psi star, right. And what is this? That is nothing but the expectation value of A, right. So, therefore, this expectation value of A into expectation value of A, I have forgotten to put the negative sign, it should be there. So, therefore, minus A expectation value square is what this term is, fine. And you look at the next term, what is it actually? We have taken this into that, we have taken this into that. The next term will be A psi star, again this is going to be with a negative sign. So, this is the next term, right. I hope I have got things right. A operating upon psi, correct. I take it from here, and this A multiplied by psi is the term that I take, and so this is what it is. And what is this actually? A I can take out, so minus expectation value of A integral A star psi star, okay. I take the complex conjugate of this, so I will get A star psi star multiplied by psi d2, fine. And just as previously, I can transfer this A star to that psi. So, if I transfer that, what is it that I am going to get? Minus A integral psi star A psi d2, and what is this? This is nothing but the expectation value of A, and therefore, what is it? You get another minus A square. And what is the last term? Last term is obtained from this into that, right. So, that is actually quite simple. Because you have the product of two negative signs, it is actually plus. So, what will happen is I will have d2 A psi star multiplied by expectation value of A into psi. Yeah, that is it. That is the last term. But there you know that A is a real number, so therefore star does not affect it. This is a real number, so this and that together they may be taken out. So, I will get A expectation value of A square multiplied by integral psi star psi, but we are assuming that psi is a function that is normalized, and therefore, this integral is 1, and therefore, what happens? The final answer that I get is expectation value of A square. So, interesting, we have 4 terms. The first term is actually nothing but the expectation value of A square. The second 2 terms are actually identical, right. You get the same answer for the second two terms and to the last term is a square. So, if you added the 4 terms together, what is the answer that you get? I can write it here. If you added the 4 terms, what do you get? You get expectation value of a square minus expectation value of a square, that is all, correct, because there were 2 with the negative sign, 2 expectation value of a square with negative signs and 1 with the positive sign, and therefore the net result is this, and therefore what is it? I mean, whatever I wanted to show, I have achieved. In what sense? I claimed that delta A square, if I define it to be like this, it is nothing but our previous definition, right. This is something, this is the way we defined delta A square in the previous lecture. So, if that is the way it is, okay, suppose I take your operator B and I am going to define something which will be B minus expectation value of B, correct, and I will say that I have delta B which is defined to be this, right, and if this delta B operates upon psi and delta B operates upon psi, once more you take its complex conjugate, integrate over the entire space, what will happen? The answer will be actually equal to delta B square, the uncertainty in B, correct, when square of the uncertainty in B. Right. If you agree with that, then I am going to make a slight modification by introducing an I here. If I had put an I there, what is going to happen? I am going to get, I am going to take its star, so it will come out and it is going to be minus I. I have to neutralize that, right, I mean I cannot just have an I minus I, so I will put another I here, so that the two everything combined together will give me a plus 1. So, I have not done anything. So, therefore, this also is valid, right. I mean these are simple mathematical manipulations. The reason for doing this is not obvious at this moment, but you will get that answer, which is what we want anyway. So, what I am going to do now is, okay, this is correct, and now I have this Schwarz inequality. This is valid for any u and v. So, what will I do? I will say that u is going to be delta A operating upon psi, right. This is valid for any u and v. So, let me say u is delta A operating upon psi, and what is v? V I will say is I times delta B operating upon psi. I mean I can always do that, because this this Schwarz inequality is valid for any arbitrary u and v. So, I am perfectly justified in choosing whatever, I mean you can choose your own u and v, it has to be valid, because this is a general inequality that is valid. So, if you did that, what will happen? If you used that, then we have attained whatever we wanted to attain, because what we wanted to have was this is equal to, this should be equal to delta A square, that is what we wanted. So, if you use A u to be that, then this will actually be equal to delta A square, and what will this be? if you made this choice, this will be equal to delta B square, uncertainty in A square and uncertainty in B square. And now with this choice, what will happen to this part is the question, and we will work that out. It is not a difficult calculation, fairly simple. If you work it out, hopefully I will get that answer. Okay. So let me do that. So if you chose u to be this and v to be equal to that, what will happen to integral d2 u star v? What will that be? It will be actually equal to integral d2 u is how much? Delta a psi star into v, v is I into delta b psi. Correct? So you can take that I outside, you are going to get I integral d2, you are going to have a minus expectation value of a psi. You have to take the complex conjugate, so star will come here, then you will have to, there is a star here because I am taking the complex conjugate, then delta b will be b minus expectation value of b into psi. And what will be integral? What is the other integral? V star u, right? So you are going to get integral d2 v star u, and that will be equal to integral d2 v star will give me a negative sign, there will be a minus I, right, because you this is v. So if you took the star, it is going to give me a minus I delta b delta b operating upon what? Psi, then you have to take the star, then you have to have delta a operating upon psi, which actually will be equal to minus I integral d2 b minus b expectation value, you have to take the star of the whole thing, psi star a minus expectation value of a psi. And now what happens? You see, I have to add these two things up, correct? I have to add these two things up. So if you added the two things up, what is the answer that I am going to get is the question. But before I add the two up, I want to do something more. I just want to see, this whole thing is an operator, and A is a Hermitian operator, this is just a number, right. So what I can do is I can actually transfer and allow them to operate upon this. From here I can allow them to transfer to here and operate, and all that I will have to do is when I transfer I have to take the complex conjugate of that. So let me do that as an intermediate step there. So, here what is going to happen is this is going to be equal to I times integral d2, you transfer it to the and to allow it to operate upon that. So, I shall get psi star a minus expectation value of a. There is already a star, but when you transfer you will put one more star. So, double star means you get the same number, original number back. So, you get a minus expectation value of a into b minus expectation value of b into operating upon psi. That is what happens to this term, and if you did the same kind of thing with this, what will happen? You will get minus I integral d2, right. You take this, you are going to transfer this to the other side, there is already a star. When you transfer you will take one more star, and therefore what will happen, the star operation gives you back the original, the 2 star and gives you back the original, but then what will happen, you will get psi star, this is going to be transferred and it is going to operate upon here. So, you are going to get right, this you are going to transfer, you see this was originally operating upon psi star, but instead of operating upon psi star you will transfer it and you will allow it to operate upon that. And well, to be actually very clear, I should put a bracket here, because this operator is operating only upon this part, and this operator again is operating only here. So, therefore, when you transfer it, it is going from here and getting operated on that point. So, that is what happens. Okay. So, then if you added these two up, which are the ones that I should add up, these two things, you will see something interesting happening. You will see that if I added these two up, I am going to get an I integral d2 psi star, okay, this is your first term, correct. I have just written the first term and I have to write the second term. Unfortunately, there is no space there. So, maybe what I will do is I will write the whole thing up here. I will write this term once more. The first term is actually I plus I integral d2 psi star, this term, let me remove this. This term is going to be psi star a minus expectation value of a into b minus expectation value of b operating upon psi. That is the first term, and the second term is actually with negative sign integral d2 psi star b minus expectation value of b into a minus expectation value of a. So, these are the two terms. If you just added the two up, you see that I is common. Not only I, there are several things that are common. So, let me take a d2 psi star, and then you will have this product a minus expectation value of a into b minus expectation value of b minus I am combining the two terms. So, this is what results, right. I have not done anything great, I mean I have just simplified things. And then if you look at this expression, what is it that you are going to get? You will get it I times integral d2 psi star. If you multiply things out, you are going to get a into b from here, and from there you are going to get b into a. It is not in the same order. You see, a into b minus b into a is what you will get. And then you should remember that these things are numbers. As far as numbers are concerned, you can put them in any order you like. They are not operators, and therefore you, for example, will get minus a expectation value of a into b, and you will get a similar kind of term from here. What is it that I said? Minus expectation value of a into b, correct? And from here you are going to get minus expectation value of a into b, but with a positive sign. So, they will cancel each other. Similarly, all the other terms, you can just expand, you will see that all the other terms except these two terms will cancel each other, and therefore, what happens? You get this as the answer. So, we have evaluated this part. What is the answer? The answer is that, and therefore, if I just substituted that to the right hand side, what am I going to get? I am going to get 1 by 4 I times integral d2 psi star. What is this actually? It is a b minus b a, and this is the thing that we have been referring to as the commutator of a and b. So, therefore, you get a commutator b. This is just shorthand notation, right, and then I have to put psi here and to close the bracket. So, this is the object that I have written, but I remember I have a square here. So, therefore, we have evaluated the right hand side evaluates to be this. On the left hand side, this is delta a square, this is delta b square. So, it says that delta a square into delta b square has to be greater than or equal to this object, that is what it says, but there is an I sitting inside and you have to take the square of that. So, when you take the square of that, you can remove this I and say that there should be a negative sign, correct. And if I remember correctly, we had actually, or I had actually demonstrated this by taking a to be x and b to be px, that I did yesterday. And you should realize that this is a very general thing. What does it say? It says that give me any two operators in quantum mechanics, give me any two operators, and it does not matter what the state of the system is, it does not matter, it can be any state of the system. This inequality has to be valid, and this is extremely general, right, extremely general. If you apply it to position and momentum, you will get what is referred to as the Heisenberg's uncertainty principle. So, this is a generalized uncertainty relation. This was not derived by Heisenberg, but somebody else. But Heisenberg derived this delta x into delta px is greater than or equal to h cross by 2, but this generalized uncertainty relationship was derived later, and it is valid for any a and b. Okay, that is the perfect time for me to stop for today. Thank you. I shall continue. We will use this in the next lecture. Thank you for listening.